When I told you all about the dormant Hibernate behavior on the Pico, I thought I had the techniques I needed for a remote IoT solar power project sorted. I was wrong. I need a total count for one of my sensors rather than being able to sample it at only 10 seconds every minute. This is for a solar powered project here in the UK, so staying on full power isn't really an option. There is another Hibernate function on the Pico though that we can use called deep sleep. In this sleep mode we can choose which parts of the Pico get shut down. We can keep some functions running. Hi, I'm John, your concierge to the world of the Raspberry Pi Pico, robotics, IoT and other fun tech. Please remember to subscribe and join the community. In this video I'm going to talk about my experience putting the Pico into a low power state, but retaining some functions. For example, I can use the Pico's internal real-time clock to wake the microcontroller. I can also wake it using an external stimulus from something like a DS3231, a proper real-time clock. Key for my use case is I need to be able to count an external event. The Pico counters are part of the PWM subsystem. I've talked about that in a previous video, and I'll talk about it a little bit more later. Playing with these functions is an advanced use case of the Pico. Keep watching for some advice on how to actually avoid some of my pitfalls in this and wasting a hell of a lot of time. If you like this video and it helps your learning or projects, why not drop me a cash tip using the super thanks button below the video. I'm saving these up to get myself to open source in San Francisco next year, and I appreciate your help in getting me there, and I hope to see you there too. Please hit the like button on the video and of course subscribe for more. So the concept here is very similar to what we saw when we were playing with the dormant capability of hibernating. Again, this is really about being able to run off battery and see how much we can extend the battery life by actually spending bits of time in a sleep mode. Now, when we looked at this previously, we looked at a wake, which was about 25 milliamps roughly, flashing an LED, whereas when we went into a sleep mode of dormant, we could actually get that down to below 1 milliamp. Actually, I've seen it down to about 0.7 milliamps, which is roughly what it says in the spec. If we're going into a deep sleep mode, actually we're not shutting down as much of the microcontroller, so there's still some subsystems running. So it won't surprise you that actually we're only getting down to about 1.6 milliamps. That's still not bad though. That's still a long way down from 25 milliamps. So we looked previously that running at 25 milliamps on a 500 milliamp hour battery would give you roughly 20 hours of life. And if we went into a dormant stage, we could extend that. So we're going to be dormant for 50 seconds every minute, online for only 10 seconds every minute. We can actually extend that life to 4 days and 9 hours. So what does that look like if we're doing it on deep sleep? Well, if we're in deep sleep, we still have a pretty reasonable 3 days, 20 hours. Not quite as long as dormant, but still not bad. As I talked about previously when we were looking at a dormant state, a lot of this does depend on what else you've got draining this down, particularly in that awake time. So controls, screens, sensors, Wi-Fi, these all have impact on your battery life and how much power that you're going to do. So I'm just exploring the technologies here rather than giving you the exact situation for your project. This video is sponsored by PCBWay. Do you find soldering your PCBs hard? I certainly do. So why not use PCBWay to not only fabricate your PCBs, but assemble them too? PCBWay strive to be the most professional PCB manufacturer for prototyping and low volume production work in the world, which makes them a go-to place for makers like me to help me fabricate and assemble my low volume PCBs in their own in-house production services. PCBWay have lots of options for PCB types and coatings, along with instant quotation through their website for most services. They can help with project hardware too, through 3D printing, CNC machining, sheet metal work or injection moulding. Get some inspiration from their community project site or buy some ready-made modules from the module store. Go take another look at PCBWay today. Once again, I am standing on the shoulders of giants to build this stuff, and really grateful to GitHub Coder and his projects and examples showing how Pico Sleep Demo works. And those are the ones that I've built these examples on. So my repo is still the RPI Pico dormant RTC, and I've done some extensions to that for this video. So I've got 3 examples on here around deep sleep. One, I'm going to just use the internal real-time clock on the Pico to wake it up. Then I use an external DS3231 real-time clock like we did with the dormant state. And then I'm going to actually do a really clever trick, I think, and actually count an internal signal while I'm both in a wake state and sleep state. And this is something I need for one of my projects coming up. All of the code in this example is based on the Pico SDK 151, and it requires Pico Extra's SDK 151 as well. So we're going to use a PicoW, actually is what I'm running this on. I'm not actually running any Wi-Fi code in this example. And then I'm going to flash an LED, which I'm going to attach to GPIO2. So we're basically going to flash an LED for a few seconds and then go to sleep for a minute, and then use the internal real-time clock to wake us up. So over here in the repo, I've got an examples folder, and in there I've got a whole set of examples, and we're going to have a look at the deep sleep internal RTC. So this is using that internal RTC for the Pico to wake it up. The actual code for the sleeping and wake up itself is actually over here in the source folder, because it's going to be a shared library. So let's have a look at main and what we're doing here. Well, main's a simple application. I'm going to basically flash LEDs between the sleep cycles. So I've got a little utility there to just flash the LED very basically. And then really what our main function is going to do is it's going to set up that LED. It's going to set up our deep sleep singleton. So we've got that and we can use that. And then we're basically going to keep printing out sleep, going to sleep for a minute and then resurrecting and saying how many times we resurrect and flash some LEDs. And that's all there is to it. And that's what I'm trying to do, is to make this library repeatable for me, so it's nice and easy to use without making too many mistakes. Let's have a look at the deep sleep side, because that's really where most of the work goes on here. And as you see, we've actually called this function sleep minutes here. So sleep minutes is really just telling it to go to sleep for a number of minutes and telling it that we're not actually going to use a GPIO to wake it up. So I'm using 0xFF, which basically means that my GPIO pad is way out of range and so it won't be used. The reason I'm reusing it, because I'm going to use this for a number of different wakes, and it's basically all the same code. So if we have a look at this sleep function here, where we're giving it the minutes and a wake pad, and I'll come back to wake pads on the next example. Well, we've got no real-time clock because we're using the internal real-time clock, so there's no DS3231. So we're going to basically set up the real-time clock. And I do a little bit of a trick here where I only set up the real-time clock if it hasn't already been initialized, it isn't already running. If it is running, I will basically get the time, add a minute to it, and then set that as an alarm. With real-time clock alarm callbacks, you can actually set everything that you don't care about to be -1, and then it won't match. So we can work on this and just worry about the minute and seconds are all we need in order to do a 1 minute callback on this. And when we call RTC set alarm, we're basically setting up an IRQ callback, and it's that IRQ which will the interrupt which will wake the processor back up. So sleep function is really because we're not using a wake pad, it's just going to ignore that wake pad number, and it's basically just going to go down and run through these 3 lines only. It's going to switch the clock to be on its internal crystal. That's what the XOSC bit is. It's going to then sleep until it hears an interrupt, and then it's going to recover the clocks, basically, which is recover from sleep, because after coming back, the clocks are not reset properly as they were in the dormant phase. So, you know, with very similar code here. So let's have a look at the sleep until interrupt, because that's really the big bit of this that's actually different from doing this in dormant mode. So sleep until interrupts. Well, what we basically are going to do here is first of all turn off the various clocks. So we use this clock hardware sleep enabled on, I think the 0 is there meaning core 0. Well, that's my understanding as well, because we're going to do the same for core 1. So on core 0, we're basically going to say we'd like to have the real-time clock still running, please. Whereas on core 1, we're actually going to have nothing running. And that's really what deep sleep is about. It's about turning off the various clocks. Now you'll see here, and I will show you in a little while, actually we could enable a few other clocks, and I've got an idea for that later, so we'll come back to that. Then really what sets the clock to go, or the Pico to go to sleep, is initiating this function to actually switch the processor into this deep sleep mode by setting that bit, and then when we go into this little loop here by issuing that command, we actually will drop into a deep sleep. So here, as I run up the example, we can see that the processor starts, it says go, and it will then drop into a sleep mode and say it's gone to sleep, and then a minute later it will resurrect. I'll just cut the video so we can see the resurrection point, because it's a little bit boring just waiting and talking here for a minute. And we can also have a look at the current draw, and you can see the roughly 25 milliamps average. I've used while we're flashing the LED, and then we're dropping down to 1.4 milliamps there while we're in that deep sleep mode. In this second example, I'm going to now add to our Pico and our LED a DS3231 external real-time clock, the ChronoDot version 2, and I'm going to use that as an external signal to wake up our Pico. Now, of course, we could actually use any external IRQ interrupt on a GPIO pad to wake this up. I just happen to be using a real-time clock in this example. Now, we can also come back from a deep sleep using external GPIO interrupts, and that's what we're going to do on this example, and that interrupt's actually going to come from an external real-time clock, the DS3231. So let's have a look at main on this example then, and you'll see it's very similar. We're going to again have a flashing unit, so we're going to flash LEDs a lot. The difference this time is we're going to set up my library for and my class for a real-time clock for the DS3231, as I did in the Hibernate example in that video. And going into dormant, that's exactly what we're doing there. And you'll see that we're going to then give my deep sleep that real-time clock to use for waking up. And the final thing we need to do that's different in this is when we go to sleep, this time we're going to sleep for 1 minute again, but we're going to give it a wake pad. We're going to tell it how that DS3231 is connected back to the processor and what pin it's using in order to wake it up again. And that's the IRQ coming out of that real-time clock. So over in sleep, let's have a look at, or open in deep sleep, let's have a look at this sleep function. How does this change if we've got a real-time clock then? What we're doing here then is we're actually going to set the delay time that we actually want the real-time clock to work, and that's all I'm doing. I'm working with the real-time clock to say, hey real-time clock, clear any alarms you've got set a delay for this number of minutes and trigger a interrupt at that point. And that's all we have to do there. So how does that then drop down into, and then, oh sorry, actually let me talk about the wake bit first. When we come out of this, we are going to clear any alarm that have been raised. So let's have a quick look at sleep, because sleep's got a little bit more code now. When we go to sleep, we've now got an interrupt that we want to fire to wake it up. And that interrupt pad, it needs to be set up. So we're going to have to set that up as we did with the Hibernate. So initializing that pad, we're going to have to pull it up because the GPIO is pulled down by the external clock, set its direction to be input, and then we are going to basically enable the interrupts. Now one of the problems with IRQs and interrupts for callbacks on GPIO, I think on the Pico, is that you can only have one function to do it per core. One callback function, however many GPIOs you're using for interrupts. Now that means with libraries like this, it's really difficult to write this and not overwrite stuff. So if another library was using GPIO interrupts as well, then there is a danger that if I just call this enable interrupts with callback function, actually I'd overwrite the existing function that I've set up. This is a bit of a pain, so I've tried to get around this a bit by allowing myself to actually just enable it, because I don't actually care. I'm not going to run any code when I actually recover from this callback. Just the act of the interrupt firing is enough to actually wake up the processor. So I don't actually need a callback function there. I just do, there must be one registered, otherwise the Pico won't run the interrupt properly. The other bit around this, I guess, is that when you recover, because we want to be nice and battery low and things, we're going to just turn off interrupts and we're going to disable the pull-up. So we're just sort of being good citizens and not setting things up and clearing them down. So finally, I guess, is when we go into the sleep until recovery, we've now got a real-time clock, so we don't actually need to enable the internal real-time clock. So in actual fact, we now may be in a situation where we are actually turning off all of the clocks for core 0 as well as core 1. The X clocks there is whatever I've set it to. By default it's 0. We could add in other clocks there, and we'll come back to that in a second when we look at the counting example. I'll skip showing this running because it really doesn't actually look much different to the previous example, but all we're doing is just coming back from an external interrupt from an external real-time clock. So what really got me going down this line is because I wanted to be able to count the number of signals I'm getting from a switch, which is going to be on a particular sensor project that I'm doing. Now normally I just set that up as an interrupt and run some code around the interrupt callback routine to just increment my counter. Easy. But of course, as soon as I go to sleep, then I will no longer be able to use that, or I would use that so that every time I get a new signal I have to wake up the processor using a lot of battery power. Now I can actually use a subsystem of the Pico to do this for me. I can use the PWM subsystem, which is kind of interesting because I always think of pulse width modulation as being about signals going out to things rather than reading back as a counter. But actually on the Pico we've got counters there. and we can set that up. All we need to do is basically initialize the pin, set it to be an input, crucially, and then go through the enable code for PWM. To get this to work, you can only do this on a pin that is enabled for slicer channel B. And if you remember my video a little while ago on PWM, you'll remember that there are 8 slicers on a Pico, that each slicer has an A and a B channel. And we could actually put PWM signals out on the A and B channel, which means that you can do 16 PWM signals off a Pico. But we can only sense and use a counter on the B channel, therefore only 8 pins. And it's a specific 8 pins that we can map these B channel slicers to. So pick the right one, otherwise this magic doesn't work. So deep sleep count. Right, well, I guess this really isn't so much about deep sleep. It's actually about how actually you set up PWC for counting. But let's have a little talk through this. So the main, again, is very similar for this. We're going to flash LEDs in between. The real new bit here is that we're going to set up a particular GPIO pad to be a counter using the PWM counting capability. So I'm going to set up that PWM. It's going to be pulled up so that we actually can count as the line is pulled to 0. One of the things here I've already mentioned is that these only work on B channels, so I'm going to just check that it's a B channel there. For the slicer, we're going to have to remember the slicer number, because actually we're going to do everything based on the slicer. And then we're going to go through and do a little bit of configuration of that slicer, basically putting it into a mode where it is counting, and it's counting on falling edge of this signal, and enabling the slicer, really, is all that's going on there. That then means that when we can do this function down here, when I do my print in my before we go to sleep, I can actually get the count number from that slicer. And that will tell me how many times that button has been pressed. And it will keep counting while it's asleep. So I'm also going to print the same thing when we come back up again to resurrected. So we'll see the number of counts we're getting while we're awake and the number of counts we're getting while we're asleep. The final bit on here, a bit of magic, is our deep sleep. I need to tell deep sleep that I'm enabling PWM, and that's really quite important, because that's what's going to leave the PWM subsystem turned on. And it won't particularly surprise you is the way that we leave the PWM system turned on is we're going to set that X clocks variable that we were looking at in the previous example, and I keep on using to set clocks because I'm going to set it to include the mask for the PWM bits, which means that the PWM subsystem will be turned on core 0. And so then when we go into the sleep until interrupt routine, we're going through this line here, and we're going to set that clock or sleep on core 0 to actually have these clocks turned on, and the clock that's going to be turned on is PWM. So I'm going to run this as an example, and I'm going to hit that switch several times, in fact 7 times, before we go to sleep. So when we go to sleep, we've already got a count of 7. Now I can keep hitting that button while it's asleep, and when we resurrect and come back to awake, we're actually have increased that counter. So this is nice. I can keep that counter running and count both when I'm asleep and when I'm awake, which means I have continuous monitoring of this sensor. Working with dormant and sleep modes really isn't for the faint-hearted. This is quite hard work to do things like debug. For a start, debug code and the processor's behavior in true debug with SWD plugged in and running GDB against it won't really work properly at all. In fact, the processor won't actually go into a sleep or dormant mode. It will go through some other pieces of code to simulate that, which doesn't really help you debug and work out what the hell's going wrong. The other bit is you can't even get standard I/O to work, because until all of those clocks have recovered and until the standard I/O routines have been reinitialized, you haven't got standard I/O for printing out text of what's going on either. So your best strategy really in debugging this is simply to be able to turn on LEDs via GPIO pads, which is quite basic for trying to debug where the code's gone wrong and what's actually happened. So this does take some patience and quite a lot of work to understand what's going on, which is one of the reasons I wanted to try and get this code into a library that I could reuse and I knew that actually was resilient and worked. Hopefully I've got that. The other gotcha here, and this took quite a bit of my debug time, was I find when you do an optimized build, i.e. cmake ... so what it would be a production build, and then you flash that onto the Pico, in my case via SWD, actually the Pico will then go to sleep but not recover from sleep. Strangely, this is completely different behavior to what happens if you now power cycle the Pico, because if you power cycle the Pico, all the code will work exactly as you expect and it will recover from sleep. So I spent several hours trying to debug why my Pico wouldn't come back from sleep, only to find that actually my code was perfectly fine. I just hadn't powered cycled it. This deep sleep experience is what I'm going to use for a weather station, so do keep subscribed so you don't miss that. If you like this video and it helps your learning or projects, why not drop me a cash tip using that super thanks button below the video. Remember, I'm saving things up to get myself to open source in San Francisco next year. I appreciate your help in getting me there, and I hope to see you there too. Thank you very much for watching. If you enjoyed the video, then please hit that like button and please subscribe to my channel so you don't miss the next video. Bye bye for now.